So in this video, we're going to resolve an integral using a u squared substitution instead of a u substitution. This is just going to put the idea in your head that you can think flexibly about these u substitutions. So here I have the integral of x squared over the square root of x minus 1 dx. And a legit substitution would be to let u equal x minus 1. Let u equal x minus 1 and see if things work out for you like we did in the previous video. The purpose of this example, though, is to show that you can think flexibly when you're doing a u substitution. So another possibility is to do u squared equals x minus 1. So represent x minus 1 with a u squared. And the reason for doing that would be that the square root of u squared would simplify nicely. Usually the square root of u squared equals the absolute value of u. In this case, I don't need to worry about the absolute value of u because I know that x minus 1, because it's under the radical sign, has to be non-negative. So if u squared equals a non-negative number, then the square root of a non-negative number is just going to be the square root of u. U's non-negative. So there's a nice simplification that happens here. If we did u equals x minus 1, we would wind up getting the square root of u. And we'd have to work with the u to the 1/2 in the denominator. So the idea is if we do the substitution u squared equals x minus 1, you get the square root of u squared, and you wind up getting to work with a linear u in the denominator, which is going to be very convenient. So in this case, we're going to go ahead and let u squared equals x minus 1. And we know from the previous videos we need to take the derivative with respect to x of both sides. And then I want to be careful here because this is going to be a chain rule problem. U is a function of x, and u is composed in the squaring function. So to take the derivative, we're going to get 2 times u times, then by the chain rule or implicit differentiation, we'll need to multiply by u prime, but we'll represent u prime as we have been doing in previous videos with du dx or Leibniz notation. And then the derivative with respect to x of x minus 1 is just 1, and we can multiply both sides of this relation by dx to get 1 times dx is dx, and we get twice u du equals dx. So this piece right here is important to us, and the substitution right here is important to us. So I'm going to go ahead and I'm going to step over to my integral, and I'm going to make as many substitutions as I can currently. So I'm going to go, I'm going to take the antiderivative. I don't know what x squared is. There's nothing here telling me what x squared is, so I'm just going to leave the x squared alone for the moment. And it's going to be over the square root of x minus 1, but we're doing the substitution u squared equals x minus 1. So I'm going to replace x minus 1 with u squared. And then dx is going to get replaced with twice u du. The 2 is a constant and can get factored out, which will leave just a u du right here. And then I want to recognize that u over the square root of u squared, u over the square root of u squared, is just going to be u over u equals 1 in this case. And again, I don't need the absolute value sign on there because I know x minus 1 has to be non-negative. So stepping down a line, I get 2 times the antiderivative. I wind up with this giving me a 1. I get x squared times 1 is just x squared du. And the issue is I can't integrate at this point because I now have an integral with respect to u, but I have variable x in my integral. So what I need to do is figure out what is x squared as a function of u so I can make a substitution and do my integrations. I'm going to get 2 times the antiderivative. And I'm going to step up here where I did my substitution and found that and let u squared equal x minus 1. I'm going to go ahead and solve this for x. So I'm going to get x is equal to u squared plus 1. So if I need to know what x squared is, which I do, I just square both sides of this equality. So now I know that x squared, given my substitution I made here, is going to equal u squared times u squared is u to the 4th. u squared times 1 2 times is plus 2u squared, and 1 times 1 is plus 1. So I'm going to go ahead and go back to my integral and replace the x squared that I have here with u to the fourth plus 2u squared plus 1, and this is going to be du. Now I can integrate my u variables with respect to u, so I'm going to get 2 times, and then u to the fourth when I integrate it, this is a power function, so I'm going to increase the exponent by 1. When you take the derivative, you decrease it by 1. When you integrate it, you increase it by 1. And because I have to get back what I started with, I know I need to multiply by the reciprocal so that when I take the derivative of this to check my answer, I get 1/5 times 5u to the fourth, and the 5 and the 1/5 give me 1u to the fourth. So I'm going to step through and grab each of these. So it's going to be plus, this is 2 times, u squared will become u cubed, but I need to multiply by the reciprocal of 3, which is 1/3, plus integrate 1, I get u, and then this is plus a constant of integration. And there's different ways I can approach it at this point. I could just go ahead and everywhere I see a u squared, replace it with x minus 1, or I could notice that a u shows up in all three terms and factor a u out, which I think is the probably the easier way to do it. So I'm going to get 2 times u times, I have 1/5 of u. I factored out a u, so u to the fifth will simplify to u to the fourth, plus I have 2/3. I factored out a u, so that's going to leave me with a u squared, plus I factored out a u, so it's going to leave me with plus 1, and then it's plus a constant of integration. And then the next thing I want to notice is that this is 2u, and I get 1/5, and u to the fourth is really u squared squared. And I want to think about it this way because I made the substitution up here u squared equals. So I'm going to be putting a u squared into the in here and then squaring it, and then plus my 2/3 u squared plus 1. And then if I wanted to clean things up a little bit, we could look at the 5 and the 3 in the denominator positions and say, let's multiply by 15 over 15, the common denominator over the common denominator. If I did that, I would get 2 over 15. I would get 2/15 of a u times, and then I would distribute the 15 into the parentheses. So I get 15 times 1/5 is 3 u squared squared plus 15 times 2/3 is 5 times 2 is 10 u squared plus 15 times 1 is plus 15, and each of these should have the plus the constant of integration after this. So I'm going to go ahead and step up to the top of the page, and now we'll start to substitute our values in for u. So I have 2/15 times u, but up here we saw that u squared was equal to x minus 1, so we know that u is equal to the square root of x minus 1, and from here I know x minus 1 has to be non-negative, so I don't need to put the plus or minus. So I'm just going to go 2/15 times u, but u is the square root of x minus 1 times 3 times u squared squared, so 3 times u squared, but u squared is just x minus 1, so 3 times x minus 1 squared, replacing the u squared here with the x minus 1, and then we get plus 10 times u squared, but u squared is just x minus 1, so it's 10 times x minus 1, plus the 15, close parentheses, plus the constant of integration. So now I'm going to simplify a little bit more. I'm going to get 2/15 times the square root of x minus 1 times, I get 3 times x minus 1 squared is going to be x squared minus 2x's plus 1, plus, distribute the 10 into the parentheses, I'm going to get 10x minus 10 plus 15 is plus 5, plus a constant of integration. Distribute the 3 into the parentheses, I get 2/15 times the square root of x minus 1 times 3 times x squared is 3x squared. 3 times minus 2x is minus 6x plus 10x is plus 4x. And I get 3 times 1 is 3, plus 5 is plus 8, and that's plus a constant of integration. And that's probably about as clean and simplified as I want to get it. We might consider, I'm not going to do it, but we might consider trying to factor this and see if it factors nicely. And if it did, it would actually be nice to write it in a factored form.